So welcome back. In the previous class I was talking about twisting algorithm. In this class I am going to talk about another very popular second order sliding mode control algorithm, that is called super twisting algorithm. If you check the literature of sliding mode control, so that is flooded with the super twisting algorithm, because one can able to use super twisting algorithm for various purposes, for the control design, for observer design, for differentiator design, and for all other different kind of purpose like parameter estimation, disturbance estimation. So there are several huge application of the super twisting algorithm. In next lecture we will also see that how one can able to talk about the integral sliding mode control just based on the super twisting algorithm. Okay, but in this lecture I am going to focus mainly on the super twisting algorithm. So let us discuss the super twisting algorithm. So again I am going to justify the name, same like the twisting algorithm. So here word super, it means that obviously our trajectory is more twist than the twisting algorithm along the y-axis. Now it is also very important to see that this particular algorithm, if you apply to first order system, then that will generate some kind of continuous control, and it is possible to show that in that way you can able to mitigate the chattering. Obviously you cannot able to completely remove the chattering. So in this lecture mainly I am going to concentrate on the finite time convergence of super twisting algorithm, and for that I am going to do Lyapunov analysis. So this Lyapunov analysis is actually proposed by Professor Morino, and super twisting algorithm is proposed by again Professor Levant. So this is one of the very important contribution in the field of sliding mode control literature. Okay, because I have already told you that there are huge application of the super twisting algorithm. So what is outcome? We are first trying to understand super twisting algorithm, their control law, and after that finite time convergence in the presence of the uncertainty. So in this lecture I am going to talk about a strict Lyapunov function, because in previous class I have told you that whenever we have weak Lyapunov function, then Lyapunov function only valid if there is no disturbance. And meaning of a strict Lyapunov function, or you can also tell a strong Lyapunov function, that same Lyapunov function is working in presence or absence of the disturbance. We are also going to talk about the gain selection criteria for the robust performance. Some kind of optimal kind of gain is actually suggested by Professor Levant, and during any practical application you can able to utilize that kind of gain, and you are able to see that result is very optimal. So in order to understand the need of super twisting, again I am going to connect it with the twisting. Okay, so why basically notion of twisting algorithm comes into picture? So our problem, suppose that if I have first order system, and if you design u equal to minus k signum x, signum sigma, here actually in place of x sigma is the variable, and if you keep k greater than the supremum over all t dt, maximum value of this particular disturbance, then it is possible to show that you can able to get sigma equal to 0 as t tending towards or t greater than equal to t some finite time. So in some finite time you can able to maintain sigma equal to 0, but what is difficulty? If you analyze this particular control, then at sigma equal to 0 this control is discontinuous, and we have already seen that discontinuous control can excite several unmoduled dynamics either inside the plant, in actuator side or sensor side, and due to that reason we need some kind of continuous control action. So after that proposal of twisting algorithm comes into picture, and what is main motivation of twisting algorithm? To convert discontinuous control into continuous control. So what was the strategy? A strategy is you can take the higher order derivative of this. So higher order derivative is u dot plus d dot t. So here I am assuming that whatever disturbance that is differentiable as well as their derivative is bounded. So even if disturbance is not bounded, that is not a problem, but their derivative should bounded, and at that time now I am going to design u dot. And how basically we are going to design the u dot? U dot I am going to design the information of the variable sigma and their rate of change. Okay, it means that sigma and sigma dot both are required to generate continuous control for first order system. And obviously some kind of comment come into picture. What kind of comment? This comment is done by Professor Leonid Friedman, that suppose that if you are telling that in order to generate continuous control that sigma dot is required. So here problem is very easy. Since you know the control, you know the sigma dot, so dt is known, and if dt is known, then what is need of sliding mode control? Okay, directly you can design any PID controller in any other controller, and due to that reason some new control strategy comes into picture. And if you see carefully, so previous controller, which is known as the twisting controller, is some form of PD controller. Why I am telling this is some kind of PD controller or switch gain controller? Because you can see that I have just used the information of switch and gain, and here I am going to take the information of sine of sigma and information of derivative of sine of sigma. Okay, so just this is the modification of PD control. Now this control, which is so called super twisting control, is nothing but some kind of non-smooth PI control. You can see here how to propose PI. I am taking K1 and information of X. So basically now our plant is looks like this, but obviously you can able to talk in term of same variable. So just sake of the proof purpose I have changed the variable, but you can consistent with this variable. At that time you can see here that I have K1 sigma, PI controller I am talking about, K2 integral from 0 to t, and after that I have sigma t, sigma tau into d tau. So this is the standard expression of the simple PI controller. Now how basically this is different from the PI controller? So here I am going to just change the state sigma by x and u plus dt. So now you can see here that what we have done, x I am going to scale by some non-linear relation x power half, and after that I am going to multiply with signum x. And here what I am going to do, in place of the exact integral of some state, I am going to take their sine integral. Okay, and in this way this is nothing but non-smooth PI. Why non-smooth? Because you can able to take derivative of this, sigma is differentiable, and integral of something, integral and obviously integration is reverse process of differentiation, so easily you can able to take derivative. But here what kind of restriction? Since I have x power half, so x equal to 0, this is not differentiable. Okay, let us check the continuity. So this function is continuous. Why this is continuous? Because discontinuity only appear at x equal to 0. All other point this is basically continuous. And if signum x greater than equal to 0, you can able to see the graph, some graph like this, and actually less than 0, then graph like this. And 0, even if signum x lie between -1 to 1 at x equal to 0, but that is multiplied with x power half, and x power half is 0. Okay, and due to that reason this will coincide here, and in this way this term is continuous. So first term is continuous, and this is integration of discontinuous term. Okay, and discontinuity is only lie at 0 measure. Okay, x equal to 0, and you can able to actually remove that area, because whenever we are taking integral, what is physical interpretation of integral? That area under that curve. Okay, so x equal to 0 is just contributing 0 area, and due to that reason this is also continuous. Okay, and due to that reason super twisting generates some kind of continuous control. Now I have to justify why this is second order sliding mode control. Okay, So in order to justify that, what I am going to do, I will take second derivative of x dot, because what is definition of second order sliding mode control? That suppose if you have output equal to y equal to some x or sigma, so what happens that if you take second derivative, then control will appear and that control should be discontinuous. But what happens here, if you start with this system, first order system, and if you take y equal to x1, y equal to x, so x dot control is explicitly appear, but control is continuous. Okay, that is no longer discontinuous, and due to that reason I have to take one more derivative, and if you take one more derivative, so k2 signum x comes into picture. Okay, and due to that reason this is applicable for first order system as a control, but algorithmic form this is basically second order mode algorithm. Okay, and due to second order sliding mode control algorithm, x is 0 and x dot both equal to 0 infinite time. Okay, now you can also able to convert, because we have already seen that whenever we have PI controller, so and if you substitute that PI controller to at u, then by defining some kind of fictitious variable, system is converted into second order. Okay, again you can able to see here that somehow I am telling that disturbance is differentiable. Okay, so super twisting control will work only if you have some kind of differentiable disturbance, and boundedness condition is also required such that this k2 signum x is going to handle this disturbance. But now here there is no restriction on dt, just continuity is enough, and due to that reason super twisting can handle some kind of ramp disturbance also. Okay, because ramp disturbance if you see, then that is proportional to k into t, some kind of things like this. So disturbance can looks like this, and if you take their derivative, then their derivative is bounded. Okay, so that is the beauty of the current proposal. Classical PI controller is not able to handle the ramp disturbance, but this is able to handle the ramp disturbance. This is also able to handle some kind of time varying disturbance, which is not handled by the classical super twisting algorithm. And another important thing, that if you apply the classical PI controller, so in with classical PI controller only you can able to talk about the asymptotic stability. Here you can able to talk about the asymptotic stability of x and their rate of change both. So key concept, obviously this will produce the continuous control, because overall control is continuous whenever I have system like x dot equal to u plus dt, and here I am assuming that x belongs to R, first order plant. So if you apply super twisting for first order plant, then you will generate continuous control, and only information of x is required. This is also very important. You can see here that since you are designing some kind of PI controller, so here x information and x information if you will give, okay, then you can able to generate the control. So unlike the twisting where information of sigma, okay, so if you change this plant by x dot equal to u plus dt, so you can see that at that time u dot is nothing but minus k1 signum x and minus k2 signum x dot. So both information is required, but here in order to generate continuous control, just information of x is required, and this gain is actually proposed by Professor Levant. He has given gain condition, and after that he has actually given one explicit gain condition. So if you know the higher bound of the rate of change of disturbance, then this gain in several practical implementation we have implemented, this will give you the best result. Okay, obviously we will prove the convergence using the Lyapunov as well as geometrical method in next lecture. So Lyapunov, strict Lyapunov I am going to propose, I am going to discuss in this lecture, and after that obviously geometrical approach I am going to discuss in next class. So this is one of the excellent contribution that is given by Professor Morino. So whenever you are proposing some kind of a strict Lyapunov function, then you are also able to calculate the time of convergence. What is meaning of time of convergence? This is somehow second order algorithm. So you can start anywhere inside this space. You can able to see that at what time, obviously that is depending on initial condition, I will converge to the equilibrium point. But geometrical method, sometime obviously time calculation is there, but some explicitness is not there. Okay, so let us try to understand the strict Lyapunov function. So what is a statement of a strict Lyapunov function? I am going to take some kind of positive definite function. So for all x, this is greater than 0, 0 only at 0, and v dot x is less than 0. Okay, and now I have to prove that in presence of the disturbance d dot t, because if you see the converted system or equivalent representation of super twisting after application on this particular first order system, so that is actually I am talking about robust stability. So in presence of disturbance d dot also I am going to ensure that both x1 and x2 both equal to 0 in finite time. What is x2 here? That is nothing but L. So now I am going to establish here x and L both equal to 0 in finite time. So for that what I have done, I have basically proceed like this kind of Lyapunov function. So basically here I am assuming that L equal to x2 and x equal to x1, and then your algorithm looks like x1 dot equal to k x1 power half signum x1 plus x2, and then x2 dot, and here you can see the gain is k1 and k2. So same gain you can write here. So that is nothing but k2 signum x1. Okay, so mathematically there is no difference between variable x2 and L, there is no difference between variable x1 and L. Okay, and after that now you can see that I have constructed this kind of state. What is beauty of construction of this state? You can able to see that this nonlinear problem, this is highly nonlinear system that is converted into linear like problem. Okay, and here this transformation is good enough at each and every point, but that is not differentiable at x1 equal to 0. Okay, so I have to treat x1 equal to 0 separately, and this is the Lyapunov function. So what we have done, we have taken some kind of positive symmetric definite matrix. So P is some kind of a square matrix, so that will satisfy P equal to P transpose, and we are assuming that P transpose is greater than 0. It means that all eigenvalue of this P matrix are strictly positive. Now you can see that in place of zeta transpose I have substituted a square root of x1 signum x1, and then we have solved it, and finally we will get Lyapunov function like this. So what is key inside of this Lyapunov function? Obviously this is differentiable almost everywhere except at x1 not equal to 0, and due to that reason I have to actually analyze this set. Let us try to see what is meaning of x1 equal to 0. x1 equal to 0 in two dimensional plane is nothing but this axis, x2 axis. Okay, so I know that Lyapunov strategy, whatever I am going to propose, that is valid everywhere, but that is not valid at this point x1 equal to 0. It means that I cannot able to talk or comment about the convergence. Here from algorithm you can try to see that x1 equal to 0, then obviously this term will disappear, because here x1 equal to 0, so and this will lie from minus 1 to 1, so multiplication is 0. Here that will lie from minus k2 to k1 at x1 equal to 0, because this is converted into differential inclusion. Now x1 dot equal to x2, so what kind of system I have? x1 dot equal to x2, and x2 dot is replaced by some kind of differential inclusion that is given like this. So you can see that using this differential inclusion it is possible to show that x1 equal to 0 will never maintain. Okay, and due to that reason there is no need to worry about this particular point. So now what I am going to do, I am going to take the derivative of zeta, because whenever you are going to calculate the derivative of v dot, then obviously zeta dot transpose p into zeta plus zeta transpose p into zeta dot comes into picture, and due to that reason you have to calculate the derivative of zeta. And here if you calculate the derivative of zeta, since zeta contain some kind of term like x1 power half signum x1 and x2. Okay, so this is the construction of zeta, okay, modified state, and it is possible to show if you take the derivative, then finally I will get expression like this, x power half comes out, and after that now this become a into zeta. Okay, please do this calculation by yourself, that is very easy. Now you can substitute here, so you can see that here I have nice quadratic kind of function on same state whatever Lyapunov function I have constructed, and here Q is nothing but positive symmetric definite matrix. Okay, so now you can easily able to select some kind of Q positive symmetric definite matrix, and A is Hurwitz. If you select, one can easily able to select Hurwitz by selecting K1 and K2 in such a way such that eigenvalue of A is strictly negative. In this way you can able to design K1 and K2. Okay, so if Q positive symmetric definite, and one of the easiest selection you can take the identity matrix. A you can select, and then easily I can able to select P, and once P is selected it means that you are able to get the Lyapunov function, and initially I am assuming that there is no disturbance, means there is no D dot here, but originally D dot is also here, so for that I have to actually analyze separately. Okay, so I will do that analysis in next slide. So before that I am going to comment about this. Okay, so what is comment? K1 and K2 I have to select such that this matrix A is Hurwitz, and how to make sure Hurwitz, you can just check the eigenvalue, and we know that if you select Q first, then there always exists P provided A is Hurwitz, but reverse is not always true. Okay, and due to that reason please first select Q, then try to select P, and then I am going to apply some kind of Rayleigh inequality. What is Rayleigh inequality? If you have some kind of function Vx equal to zeta transpose P into zeta, it is possible to show that is bounded by these two things. Okay, where lambda is minimum eigenvalue and lambda max is the maximum eigenvalue. Okay, and after that now Q is again positive definite function, because minus Q I am using, so I need this whole thing should be negative definite. So how to make negative definite? If I select Q positive definite, so minus of this become negative definite. Okay, so again that will satisfy exactly same relation, and I know that zeta is given like this, and due to that reason I have taken the 2 norm, that is also called Euclidean norm, so then I will get this, and in this way I can able to substitute the x power half, because if you see carefully, then somehow I have to substitute x power half in terms of V, then only I can able to talk about the finite time stability, and this also I have to substitute in terms of the V. So same kind of things I have done here, and finally I will get this kind of differential inequality, and we are already well aware, several module I have discussed that if I have this kind of differential inequality, then that is V equal to 0 in finite time. Okay, and here gamma easily you can able to check that is coming like this, and after that by comparison lemma I can able to calculate the time of convergence of this particular algorithm. Okay, so in this way explicitly I can able to get the time of convergence. Okay, now what I am going to do, I am going to actually analyze super twisting algorithm, that is also called Putter super twisting algorithm. So here whatever D I have taken, so somehow if you are going to analyze the in form of the control, so control is like this. Okay, but what people are doing, since super twisting is applicable for several other purposes, and due to that reason people has expressed super twisting in form of the algorithm. Algorithm means you can see that nowhere external input is required. Okay, and after that D dot they have just replaced by D, but whenever you are going to use as a control for first order plant, at that time you have to replace D by D, dt by D dot. Okay, but suppose if you are just want to see the algorithm, because once you apply U here, design super twisting algorithm here, as a controller, then finally that will converted into this form only, okay, where dt is nothing but d dot. But in form of algorithm that looks like this. Now I have to analyze the stability in presence of this disturbance dt. I am assuming that dt is actually bonded disturbance. That kind of things I am assuming. Okay, some bond delta 0. So here you can see that I have actually assumed some kind of bond for that. So now what I am going to do, that bond I have assumed as a mu. Okay, dt signum x1 I have assumed as a mu. Okay, so mu is bonded by d0. So now I am going to utilize exactly same Lyapunov function, because I have already told you that whatever Lyapunov function I am going to construct, that is a strict Lyapunov function. And what is meaning of a strict Lyapunov function? That same Lyapunov function is valid in presence of or absence of the disturbance. Okay, again I will calculate the derivative. What kind of modification comes into picture? Mu will come here. And you can see that mu is not a simple term, that is depending on time. So now I have to prove for all mu this matrix is somehow Hurwitz. Okay, and that is not a easy problem. Okay, so for that what I am going to do, again I am going to perform the Lyapunov analysis. Delta A, what I am going to do, A is unperturbed part and delta A is the perturbed part, because this matrix I can easily able to write in the combination of A plus delta A, and all uncertainty I am going to actually keep inside this matrix delta A. Now I have to show that in presence of delta A is varying because mu is varying with respect to time. I can able to prove that x1 and x2 both equal to 0 in finite time, some t greater than equal to t, and obviously that is depending on the initial condition of x1 and x2 0. That kind of things I have to prove. Okay, so what I am going to do, for that I am going to apply some kind of criteria that is already exist in the robust control literature. And what robust control literature is suggesting, suppose that A0, this matrix is known, and delta t, that is unknown. Okay, so system is called quadratically stable over delta if there exists P such that for all delta t, that is depending on time, so this condition will satisfy. And now it means that stability will preserve for all delta t if this condition will satisfy for all delta t. So solution of this equation is very difficult because delta t is varying with respect to time, and due to that reason some equivalent conversion is required. Okay, some kind of equation that is called algebraic Riccati equation is required, because this kind of equation is easily solved using any software, any MATLAB software or any other software. So what I am going to do now, I am going to actually take A dash, and this term I am going to split into 3 terms. Okay, so D is known to us, E is known to us, because mu I am assuming that mu is upper bounded by mu and this is bar. So now mu by mu bar, since mu bar is upper bound, so it is possible to show that this term is going to lie between, absolute value of this term is going to lie between 0 to 1. Okay. Now this lemma is very important, that is called bonding lemma. So you can see that what is beauty of this lemma, here x and y is involved, y and x is involved, but in right side x and y become separated, and this R is nothing but some kind of positive definite matrix. What is meaning of positive symmetric definite matrix? R equal to R transpose and R greater than 0, means all eigenvalue of this matrix is greater than 0. Now again I am going to substitute everything, and after that now what I am going to do, I am going to express this delta A in terms of the D, Ft and E, and R I am going to select as a epsilon. Epsilon is some kind of parameter that is greater than equal to 1 as, and I as a identity matrix. So obviously this is positive definite, easily you can able to check. So this is nothing but 2 cross 2 identity matrix. Okay. After that now I am going to substitute it, and you can see here that every term is definite now. So I will get a standard algebraic Riccati equation. So I can able to always maintain that is equal to minus q, and in this way I can able to prove the stability of super twisting algorithm, okay, in presence of disturbance, provided disturbance is bounded. Okay. and this result is very useful for several practical purposes. Okay. So now what I am going to do, I am going to take some kind of the single tank model. This model is actually available in our lab. Okay. So we have two configuration. So in first configuration it is possible to show that tank system is just modeled by first order differential equation. Okay. And when two tank is connected, then that is called second order system. So I am just going to take the first order system, because what we have seen that if we have first order system and if this disturbance is differentiable, then I can able to, and obviously bounded, then we can able to apply some kind of super twisting algorithm, and form of super twisting algorithm is given by x power half signum x, and after that this is integral from 0 to t k2 sine of signum x1 into dt. In this way I can able to design the control. Okay. So what we have done, in form of voltage we are going to represent inflow, and this is nothing but Bernoulli equation, and inflow and outflow that we have represented like this, and finally it is possible to show that rate of change A1 is the cross section area, L1 is the length. You can, if you equate this, then you will get this kind of model. Always we have some kind of uncertainty. You can assume that this uncertainty is differentiable and bounded. Now what is our aim? I want to maintain LDS equal to some kind of reference that is called 15 centimeter. Okay. So I have defined the error in terms of sigma dot I have defined, and after that we have designed the super twisting algorithm considering this disturbance, and you can see that in finite time I can able to track this particular level, and whatever voltage I have to apply, that is also basically continuous. Okay. So in this way I can able to apply the continuous super twisting algorithm to first order plant. Okay. So chattering one can able to minimize. Now since control is continuous, so means this comment is actually theoretically there is no chattering, but it is possible to show that during hardware implementation, so hardware implementation of fractional term is always creating some kind of difficulty. Okay. And due to that reason some kind of perturbation you can able to see during the input output. Okay. So this comment is little harsh, and after that obviously finite time convergence, and only requirement of x is required whenever. So if you have first order plant, so only one information is required, and you have to select gain like this. So if you select gain like this, it is possible to show that whatever matrix I have constructed, that is also Hurwitz. Okay. And obviously you can able to see that adaptive super twisting algorithm is also already given by Professor Utkin, and after that that is able to handle time varying disturbance. And combination of neural network also several places people are using, okay, for the super twisting algorithm. So you can able to utilize super twisting algorithm whenever you have some kind of ramp uncertainty. Okay, that is also one of the very good application, and obviously you can able to maintain the finite time stability. Okay. So with this whole remark I am going to end this class. Thank you.